Welcome, structure students. Today we're going to be going over influence lines, and so I wanted to give you a little bit of introduction to why we use influence lines. Influence lines mainly mainly used for bridges. So influence lines involve a moving point load, and so for buildings and structures and things for the most part, we don't need influence lines unless you have, for some reason, some moving load across your structure. But bridges definitely have moving loads across the structure, large ones from the trucks that we drive across them every day. So influence lines mainly used for bridges. We'll get into some of our learning outcomes and such soon. But I wanted to give you a little bit of the feel for moving from country to country. So today we're making our travel from Machu Picchu, Peru, over to the state or principality of Palanan, Isabela in the Philippines. And so there you can see the journey. I'm using a previous presentation from one of my students, Natalie Cox, who graduated a few years back. So Palanan, Isabela is in the Philippines. So there's the Philippines in the world, and you can see the location of where this bridge is. And so the population is 17,000 people. It's the 10th richest province in the Philippines, and is known for a lot of agriculture. The province is named after Queen Isabella II of Spain. And just one of the things about the city is very rural, and there are little to no roads connecting Palanan to neighboring cities. So really, when they built this bridge, the Deben Benin Bridge, I'm not sure if I got the pronunciation right there. It was really, something that the folks were looking forward to, because they often had, like, what you see here is kind of like the arroyos that we have in San Angelo, Texas. It's, an area that floods very frequently. And so this allows a rural community, even during the flooding periods or the monsoon seasons, to still get across the bridge and get to neighboring cities and still be able to do commerce and such like that. Unfortunately, the bridge was originally proposed in 2007, but by 2015, it was still in incomplete and poor condition. So you can see the picture on the bottom left. That is from 2015, so just not a good situation. It seemed like the construction was pretty much abandoned. So even though it was abandoned, residents still, you know, took the risk of traveling across it for transporting some of their goods and other food items to neighboring villages. And so they were unfortunately also being taxed on it. You can see here a worker crossing kind of a board bridge. And at the time of this presentation, 2018, it was kind of unknown whether or not, I guess this was 2019, it was unknown whether or not the bridge would be completed or reconstructed. And so they call it the Broken Bridge, and you can check out this YouTube video. Basically, you'll see, kind of people on like little motorbikes shadily crossing some of those wooden plank areas, still trying to use the bridge to get from one side to the other. So that is kind of the situation where it was. Luckily, the bridge was completed in 2021, and so things were updated. Everything was connected a little bit better, a little bit smoother. So it seems like the bridge is now working for the community. So this is a good story that it finally got done. But anyhow, so hopefully that was interesting. We'll go ahead and take a look at our learning objectives and our different items of business for influence lines. All right, so today we're going to talk about influence lines. So our main learning objectives is to explain the function of influence lines in structural engineering, and then to be able to draw influence lines and use them to determine response magnitudes. So, well, to date, we have considered only stationary loads acting on the structures. And so when we think about like shear moment diagrams, right? Shear moment diagrams allow us to plot the response of axial force, shear, and moment at all points on a structure just due to one loading situation. And so what we want to do with influence lines is not look at just one loading situation. We want to plot the response for, a moving load, but because the load is moving, we can only plot the response for one specific item or one specific point. So For instance, the influence line could be plotted for reactions, internal forces, deflections, and other structural responses. And so to do this, we're going to employ the following methods. The two methods are the equilibrium method. So as always, the equilibrium always applies. And so we are just going to move this unit load, this one kip load around, and we can do equilibrium to find the response at a particular point. The other one will be the Mueller-Breslau principle, and so hopefully that will be, hopefully you'll get that, especially if you're good at dynamics. We'll be doing like kind of rigid body motion to solve this. And so let's go ahead and look at example 1A. So we're asked to draw the influence line for the reaction at A. And then we're asked, what is the reaction at A if a 32 kip point load is placed at C? All right, so I'm going to look for the influence line for the reaction at A. So we're going to draw in our reaction AY. And so what we're going to look at is how do we solve this reaction AY as this one kip moves across the structure. For reference, I'll also put in BY. So I'm going to create a little table for this. And so I'm just going to set up a little table that's going to be we're going to change the value of x, which is the distance from point A. And we're going to look at what the reaction at AY is. And then we'll plot that on the graph below. And so here's the table. I have my distance x, and then I have the reaction AY. So when x equals 0 feet, so the one kip load is directly at point A, AY is going to be one kip. So hopefully this is pretty easy to solve from statics. I think another obvious one is when x equals 10 feet. The one kip point load would be directly over point B. Then our reaction at A is 0. So when it's at A, reaction is 1. At B, it's 0. If we went halfway between here, so this is a 10-foot long beam halfway, right, we would expect the reactions at A and B to both be 0.5. And lastly, we can put it at point C, which is x equals 7.5 feet. We see here that the reaction is now 0.25 kips. And you could solve this by just using equilibrium. So some moments about B to solve for AY. I'm going to plot these values now on a graph. So this graph for the influence line of AY just means when that moving unit load, that unit one kip load, is at these different spots, we can track what the values are. And so we'll see that for determinant structures, so right now we're dealing with determinant structures, and we're just going to mainly look at influence lines for determinant structures. The influence line should always be a straight line. And so you see here that when I plot this response, I get this straight line connecting from A to B. All right, so the second part of the question asks is, what if we place a 32 kip load at point C? What is the value for the reaction AY? And so this is really the use of influence lines, is because we have different loads, and we use that one kip load so that we can scale this up accordingly when we have other values. So when we place the 32 kip point load at x equals 7.5 feet, we see that the value of the influence line at that point is 0.25. And so we will take the value of the influence line at 7.5 feet and then multiply that by our point load of 32 kips. And that will solve for the reaction at AY. And so this is useful as you have different moving loads, maybe across your beam or across your bridge, to solve for the reaction under different loads. All right, the next part of the example really looks at us considering a distributed load. And so we have now a 5 kip per foot distributed load from A to D, which is now in the middle of the bridge. How would we solve for the reaction at point A? So we have a couple different options. And so we can basically just resketch our influence line from example 1A. All right, so the first option is what we're pretty used to, is coming up with the resultant force, right? And so we can actually use the value of the resultant force, and if we place it at the center of gravity for that particular distributed load, we are able then to match up where that resultant force hits the influence line. We will be able to figure out what the response is at for the reaction AY. So we see that the resultant force here is in the middle, so it'd be 2.5 feet. We then have to just come down to our influence line, figure out what the value is at that point. So that value would be 0.75. You can always use similar triangles to find out what this value would be. I think it's, in this example, fairly obvious. And so we then can solve for the reaction AY. And so we take our value of the influence line at 2.5 feet and we multiply it by the total resultant force. So that's going to be 0.75 times the 25 kip resultant force. And do the math. That should come out to about 18.75 kips. Alternatively, we can actually take the area under the influence line over that span from A to D. We can take the area under the influence line and multiply that by the value of the distributed load, the 5 kips per feet. And so we will go ahead and take a look at what those values are. So I'll go ahead and shade that area in red. I'm going to break up the area of the trapezoid into an area of a rectangle and an area of a triangle. The height of the rectangle will be 0.5, and then the height of the triangle is also 0.5. And so taking the areas for the rectangle, we have 0.5 times 5 feet. And for the triangle, we have 1/2 times the 0.5 times 5 feet. So the 1/2 just coming in for the area formula for the triangle. We multiply that all by the distributed load of 5 kips per feet. And so now we can run the numbers on the calculation here. 0.5 times 5 is 2.5. 1/2 times 0.5 times 5 gives us 1.25. And so if we type this in our calculator, we see that AY is now 18.75 kips. Same answer as before, so hopefully we're expecting the same answer. And so either way, both of these methods will get you to the same answer for AY.